Okay, please note that you're being recorded from now on. Good. Okay, so today we're going to talk about the independent sample t-test. We're continuing today. Do you see my screen? Is that fine? Hope audio and visual both is fine. Session is being recorded. Okay, we're continuing talking about the t-distribution, more specifically the independent sample t-test today. Just as a quick recap, last time we did dependent sample t-test, which was a continuation of the one sample t-test. So again, so we came from the STAT test, where we basically compared sample mean to a population mean, and we subtracted this difference. So we subtracted the population mean from the sample mean. We utilized the standard deviation of the population, the actual given standard deviation that was known, to characterize and standardize this distribution of the mean, so mean differences, where we subtracted then the respective population mean from. And we utilized this for hypothesis testing, whether this difference was this difference was actually a significant difference between the sample mean and the population mean. For the STAT test, characteristically, you have the standard deviation of the population given. Now we moved on to the one sample t-test, where we're utilizing the t-distribution to estimate the distribution and the variability of the population by estimating it based on the standard deviation of the sample. This is calculated differently, and we introduced the thought of the degrees of freedom, where now the variance is not divided by the degrees of freedom rather than the sample size. Consequently, we get an artificially inflated estimate of this standard deviation, which is more likely to represent or reflect the standard deviation as you would find it in the population. The standardization is the same. We're dividing then the derived standard deviation by the sample size, and we get to the standard error of the mean, which is meant to standardize this distribution of mean, standardization of the mean differences. In the context of the one sample t-test, we compare one sample to the population mean or any other reference value. In the dependent samples t-test, we're comparing two chronological conditions, so before and after situation, for example, measurements of population means at two different time points by calculating individual scores differences within a sample that is being followed over time. We're standardizing these differences, these individual differences, and we're comparing these differences essentially then against the hypothesis change, which in the simplest case is 0. In some more complex cases, it's basically a predefined or anticipated change. Now with the independent samples t-test, we actually were continuing this thought process further. And now with the dependent sample t-test or paired sample t-test, we studied a within groups design. In an independent sample t-test, you're basically comparing two means in what is called a between groups design. So we know the between groups design in the simplest and most commonly seen format. It's two different cohorts, which can be randomized or non-randomized. But in the most characteristic kind of study design, we're talking about a randomized controlled trial, where we basically have a control group and an intervention group. Notably, the dependent variable is then on the y-axis, that variable that you're interested in, be it blood pressure, be it cholesterol, be it happiness, as we will see in a few, wine ratings, as today's example will show. So whatever scale dependent variable you may have at hand for your research question. The independent variable is now, as it was with the dependent sample t-test, it was time. It was before and after. This became your independent variable. Whereas in the independent sample t-test, it's the actual group allocation. So if you have on the y-axis a scale variable and on the x-axis as the group variable, a nominal variable, which is intervention group and control group, you're comparing the distribution on the y-axis between two groups that are basically depicted on the x-axis. And we have seen that with various visual displays we have looked at in chapter 4. A classical example would be this box whisker plot or the violin plot. So independent sample t-tests are used in the between groups design and essentially are being used in a situation in which each participant is assigned to only one condition. So this being said, here's the example of happiness scores. So let's assume each individual in this group gave a statement of happiness. And you have two different groups. You have one condition gives us assessment of their happiness, and you have a second group that gives an assessment of their happiness. So you have a certain sample size in both groups. And conceptually, how you have to look at this is you're taking then a subsample out of these samples, and you calculate a difference of that subsample. You're dropping the sample back and you only keep the difference. And you do this repeatedly, and that will help you to get an estimate of the distribution of these differences between the two samples. And this will basically be the distribution we're using now to compare these two means. So we're taking random samples from our two populations, and these samples will allow for us to characterize and standardize our differences between those two means. And the principle is essentially the same as with other tests. We're getting a mean. We're characterizing the differences between these two means by randomly sampling and randomly calculating the differences between those random samples, and then basically characterizing the distribution of these differences. So what we see here is basically mean differences between two samples of happiness scores. So we're seeing here the differences, and this is the distribution of these differences. And we're testing this against a mean of 0, which would indicate under our null hypothesis that there's no difference between those two samples. And this is basically how we're approaching this in an independent sample t-test. So again, two groups, random samples, and they basically give us for each random sample that you're pulling out, you get a pair out, you calculate the difference, you characterize the distribution of these differences. And this is how we will approach this. So the steps for doing this independent sample t-test is again the same as we've always done. So it's the same 6 steps. So we identify the populations. So we need to know which one is in that group and which population is in the second group. We need to characterize the distributions by calculating central tendency and variability. So we need to calculate the mean and the standard deviation. Then we're going to make the assumptions that are being necessary for a t-test, so independent samples, randomly drawn, randomly sampled, and the normal distribution. We have a null and a research hypothesis. Well, basically the null hypothesis, again, tells us there's no difference between those two groups, whereas the research hypothesis tells us that there is a difference. The same principle applies. It can be a two-sided test or it can be a one-sided test. If we're hypothesizing a directional difference, you would utilize a one-sided test. But again, in 99% of cases, it will be a two-sided hypothesis, where the null hypothesis says there's no difference and the alternative hypothesis says that there's a difference in either direction. Then you determine the characteristics of the comparison distribution, and this is where you take the standard deviation and basically move this in the direction of calculating your standard error of the mean, where you basically characterize your comparison distribution of differences. You then determine your critical values and your cutoffs, which is basically done by assumption of a certain alpha, which is, as per definition, just to recall, this is the type 1 error, or the type 1 error is that rest risk of you rejecting something that you shouldn't have rejected. And the alpha is the type 1 error that you're willing to accept. And this is set at 5%. And that will basically, in the knowledge of the degrees of freedom of your sample, which is, as per definition, the sample size -1 for this last redundant entry that you could drop in the knowledge of the sum of squares. This will basically tell you what the cutoff value for your t-score will be. So beyond which, once you exceed that particular critical value, you will reject the null hypothesis and accept the research hypothesis. This also can be numerically expressed by basically calculating the confidence intervals, and this we will also do today by basically calculating around our differences confidence interval, with which we are 95% certain that the null hypothesis is actually true, and beyond which, if it doesn't contain 0, as we discussed last time, if it doesn't contain 0, we will reject the null hypothesis. Lastly, that's the last two steps. So basically calculating test statistics, and then based on the test statistics and the critical value, we will make a decision on whether we accept or reject the null hypothesis. So same outline as in previous tests, but basically the methodology will be different, and the concept of how the populations are being defined. So today's example deals with wine. So we have two populations. We have a group of people. So both populations drink the same wine. They're being served the same wine. And population number 1 is being told they're drinking a $10 bottle of wine, whereas the second population is being told they're drinking a $90 bottle of wine. So as you know, people don't, so in some certain occasions, people tend to rank wines that have a greater price tag as being the better wine, although that may not always be true. However, it creates some certain assumptions once you pay a higher price for a wine. So this is being put to the test. So we have a population of 4 individuals that drink a $10 bottle of wine, or are being told to drink a $10 bottle of wine. And we have 5 individuals that are being told to drink a $90 bottle of wine. The comparison distribution is a distribution of differences between means. So we have these two means, and we're calculating these differences. We're calculating difference between those two means. And then we're basically assuming what the variability of these means essentially would be, given that sample size that we have at hand. So it's now not a distribution of mean difference scores as we had for the dependent sample t-test, but now it's basically a distribution around the differences between those means. So again, we have 2 samples, and we assume with a certain sample size that given the variability that we're estimating a population would have, we're estimating a certain variability of random samples that create a distribution of means. We're estimating what this variability of the means likely would be if we would have drawn random samples. So the assumptions here basically point to an interesting fact, which comes back to why randomization between 2 groups is very important. So if you have 2 samples, 2 random samples that you have drawn, that you serve that wine, and you have them in a non-randomized setting, you have a certain distribution between both samples. That means you may, for some interesting reason, you may have a group of sommeliers that are basically being served a $10 bottle of wine, and they will have a more accurate rating of that wine, whereas you have in the second group that think they're drinking $90 bottles of wine, you basically have non-wine connoisseurs that don't know much about wine and they're just so impressed by the price. That would be one of these settings where the knowledge about wine would actually serve as a confounding variable confounding the insights you get from your design. That's why randomization and creating two randomized sample populations would essentially allow you to be sure about having an equal distribution of these confounding variables between those two randomized samples. So in our case, they're not randomly selected. So therefore, we need to be cautious with respect to generalization of our findings, because there may a confounding variable be unequally distributed. So that's a possibility. Second assumptions that we cannot be sure about is we don't know whether the population is normally distributed, or whether there could be in that estimate hypothetically be a certain ceiling effect, because the rating will likely be only following a certain scale with a certain range. So we cannot be sure that the population is actually really normally distributed. However, these are assumptions that at this point we have to somewhat take into consideration, but it will not prevent us from utilizing an independent sample t-test. So before we get started, Nolan and Heinz want us to quickly review the different tests. So I briefly alluded to this before. So we basically, at this point in time, we've dealt with 4 different hypothesis tests. The first one, which we discussed, was the STAT test as the simplest of our tests. So we have one sample, one mean that we're comparing to a population mean. Characteristic is that the comparison distribution is here a distribution of means, where we basically subtract the population mean as a quote-unquote constant from, and we're then utilizing the difference of this distribution of means to the population mean, utilizing the so-called standard error of the mean, which is the variability of that mean based on the standard deviation from the population. The distinction to the single sample t-test, where we also have one sample and we're following the same arithmetic approach. The difference is that for the single sample t-test, we're utilizing the t-distribution to actually estimate the standard deviation of the population by utilizing a different formula for the estimation of the standard deviation, which basically modifies and inflates the wideness of the distribution, thereby more likely reflecting something close to the standard deviation to be expected from the population. With the paired sample t-test, we have 2 samples. However, what's different, or what's important to keep in mind, is that these 2 samples are actually the same individuals. So essentially what you are doing then was a dependent sample t-test, and we've discussed it at length in last class. We're basically calculating individual scores where we're subtracting the after condition from the before condition, and we're getting a difference in the scaled variable, and we're comparing the distribution of these mean difference scores. Now it's different. Now we have 2 groups that are in the entirely different participants. These are 2 independent samples that are being compared to each other. Now we're comparing these 2 means by testing the distribution of the differences between the means of these randomly drawn samples, and just estimating the difference based on this assumption that these differences will be varying according to the distribution in the sample. And this is essentially also the complication, because we need to factor in now both of these variabilities. So we have a standard deviation in sample 1, we have a standard deviation in sample 2. Both of these variabilities are basically determining the distribution of differences between means and the comparison of these differences between means. And that's where it's arithmetically a little bit difficult to calculate, but we will walk through that step by step, and I will explain this in much detail. So the step 2 of hypothesis testing, as we know, is again a null and a research hypothesis, whereas essentially it's easy to develop the null hypothesis. We basically have a mean 1 equals a mean 2. And which basically would say that people who are drinking the same bottle of wine, being told it's a $10 bottle of wine, will rate the wine accurately as it should be in exactly the same fashion as those that are being told it's a $90 bottle of wine. The research hypothesis is that the price actually will affect these ratings, and people that drink the $90 or purportedly $90 bottle of wine will essentially rank the wine differently, higher or lower. It's a two-tailed hypothesis, both is possible. So, and now the differences here are a little bit more complex. So there are 5 stages to that. So essentially in the first step, you basically calculate what is called here a corrected variance for each sample. So you calculate the variance that basically follows the same arithmetic principle we've done before by calculating a variance sum of squares divided by the degrees of freedom for each of those samples. So we have a variance that reflects the variability in each sample. These 2 variances then need to be pooled together and then essentially being merged together in a format that gets us to a pooled variance that is determined by the respective degrees of freedom. So we need to amalgamate all this information together to get then essentially to square root or standard deviation or standard error of the mean of these differences that allows us to really estimate the variability in these estimate of the difference, or the distribution of the difference. And this is a little bit more tricky. So, but let's do this actually with an example. So we have now in the spreadsheet, we essentially have our data. And I'm making this larger. I hope this is well to see. So we have here on the left top, we have our liking ratings. So this is the metric that Norton and Heinzen here introduced for this comparison exercise. So we have here 4 ratings of the wine that where people were told in that group it's a $10 bottle of wine, and we have 5 where people were told it's a $90 bottle of wine. This adds up to an average. So we're changing here the format. We're changing it from a so-called wide format, where each participant is 1 entry on a column. We're changing this in a so-called long format. I'm just gonna get this over there. Spread it out a bit. So again, I hope you recall how to do a transposition of these. If not, I just repeat it quickly. So if you have a situation like that, where you have a wide format and you want to change the format into a long format, the only thing you need to do is you select what you want to transpose. Transpose means basically changing direction. So you're collecting these 5 entries, including the header. You're copying it. You click in the cell you want to copy it into. You make a right click. You go on paste special, and on the paste special, you have the bullet point transpose. And if you select transpose, it will depict the data in a transposed fashion. So, this being said, what are we going to do first? So the first step is to characterize now the distribution of these entries. And the first step always will be the calculation of average. And that's fairly simple. We're basically using the average function, and we're averaging these 2 populations up. So this being said, this is fairly simple, and we get here a ranking of 2.5 and 4, just like here in column H. Now, next, we need to calculate our variance, which we know very well how to do. We know x minus m will give us the deviations. So x is here 1.5 minus the $m. Oops. Okay. So we're getting now $J $12 will get us the difference from the mean locked in with the dollar sign. So this basically makes this reference value from which you're subtracting from the respective individual entry, locks it in and will not shift it downwards. If you do this again, you get X minus M now for the $90 wine drinkers. So you basically get this minus $N $12. Good. So now we get the individual entries here for the $90 wine drinkers. We get the deviations, and now all we need to do is we're taking this deviation and we're squaring it up. Squaring it basically gets us to these squared deviations that we can now just simply copy over. There we do not need to lock anything in, because that's referencing the respective entry in that cell. So we're getting now here these squared deviations. So as we know, summing these up will basically get us the sum of squares. And this essentially will lead us to the calculation of the variance. So now the variance of X is this divided by the count of our entries. Oh, that's close, -1. That's the degree of freedom, right? And we know now, the degrees of freedom of X are basically count of all entries -1. Oops, no. That's the importance of paying attention to a parentheses. It's count -1, parentheses after count. So we have here degrees of freedom of X. So that's simple, right? That's considerably simple. So we have here again, so the degrees of freedom first, degree of freedom 4 equals count of these 5 entries -1. So that's 4. So we have now our 2 degrees of freedom. Now we want to have a variance of Y, and that's basically now the sum of squares divided by our degrees of freedom. So our variance here for Y is essentially 0.63. So that's well, let me double check this again. Oh yeah. So it's actually careful here. If you copy the formula just like I did, you need to have P6, P10. Okay, so we have now our sum of squares for both samples. We have the variance of our both samples, and we have the degrees of freedom of both our samples. And so now the situation gets a little bit tricky. Okay, so we're here. So as the next step, we need to dig a little deeper now. So now, if we're looking at these results, so we have now calculated these 2 variances. We know the degrees of freedom of X and the degrees of freedom of Y. We do have these 2 variances. And so now the next step is to calculate the so-called pooled variance. So we're pooling these variances together, and we need to then convert these pooled variances from the squared standard deviation by dividing the pooled variance by the sample size. That gets us to what is to be our standard error of the mean of these differences. So basically what we're doing here, we're calculating a proportion which basically accounts for our population X, and then we calculate a proportion that accounts to population Y, sample population Y, as a proportion in reference to degrees of freedom of total, which is degrees of freedom X plus degrees of freedom Y. So we're taking and putting weight of the respective proportion of how much that particular sample population contributes to the total degrees of freedom, and we're putting that weight on the estimate of that variance. By that, we're creating a pooled variance. What does this mean? Okay, let's copy this over, and let's do this in Excel. It's just easier to show these things essentially in Excel because it's hands-on. I strongly believe in that when it comes to statistics. So, okay, so we want a pooled variance now. Our pooled variance is now calculated as the degrees of freedom multiplied by the variance of the respective groups. Degrees of freedom of Y as a proportion of the total degrees of freedom multiplied by the variance of Y. So we have our degrees of freedom of X. We have now a degrees of freedom of total, which is essentially degrees of freedom of X plus the degrees of freedom of Y. Now we need a proportion, dfx over df total, which is basically 3 over 7. A proportion of dfy is essentially nothing else but 4 divided by our degrees of freedom of 7. So we have 0.57 as a proportion of y, with 0.43 as a proportion of x. So this adds up, as we can already assume, this adds up to 1, right? Logically. Good. Okay, so this is proportion totally. Good. So now what we want to do next, we multiply now the respective proportion of the sample to the variance of the respective sample. So to calculate our S square pooled, we would estimate this as our proportion of degrees of freedom of X multiplied by our variance of X, giving the variance from X the weight it deserves based on the degrees of freedom, adding the proportion of Y multiplied by the variance of Y. And this is our pooled standard deviation, our pooled variance. So this pooled variance then serves to estimate the variance of this difference. And this is where both of these come together. This is where both are essentially then put together and added up. So we basically have now our S square difference is now this divided by our sample size, because this is how we get to the standard error of the mean, right? So we have now our variance, and we're dividing this now by the sample size, because it's squared, and it's a squared, it's now the standard deviation. We are essentially having to square now each part of our equation, which used to be, as you remember, so standard error of the mean equals standard deviation divided by square root of the n. So now we have standard error of the mean squared equals variance or standard deviation squared divided by our sample size, not the square root of the sample size. This is why we're leaving this here as count and don't utilize the square root. So M22 is our pooled variance divided by the sample size plus the M22, which is our pooled variance divided by count of our $90.20. So this basically gives us a squared difference, squared standard error of the mean difference that essentially now allows us to calculate the standard deviation of the difference. And this is our standard error of the mean. So this essentially is now S difference is now the SQRT of exactly this value. So that gets us to 0.616. So that's our standard difference. So this is how we're getting there. So once again, we have two samples. We're calculating for each sample a mean. We're subtracting the individual score from the mean. We're squaring these individual differences, summing them up to get to the sum of squares. We get from the sum of squares to the variance. And we are then calculating a pooled variance by multiplying this proportion derived from the degrees of freedom as a proportion of the total degrees of freedom multiplied by the variance, thereby giving a weight to the respective variance from that sample, and then adding it with the weight or with this proportion from the second sample multiplied by the variance of the second sample. This gets us to a pooled variance. Then adding these up, these pooled variance, and dividing them by the respective sample size in that sample of the respective sample, either sample X or sample Y, and adding these up gets us to this pooled standard error of the mean of variability of the differences, gets us then, employing the square root on this, gets us actually to a standard error of the mean of these differences. So now it's actually more a standard deviation of the differences rather than a standard error of the mean, because it's a difference between the means. So it's not a standard error of the mean in the classical sense. However, for hypothesis testing, we are essentially now moving forward with this variability. And this is the formula that you essentially need to keep in mind for this purpose, because what we have now for the calculation of the t. So for the one sample tests, we essentially calculated a difference from a mean. With the dependent sample t-test, where we compared two samples, we basically calculated mean after, or individual score after, minus individual score before. We calculated this mean differences, this mean difference. And we subtracted from that our null hypothesis. So now we're basically doing the same thing. We have here mean X minus mean Y, and we're subtracting from that our null hypothesis, which under the null hypothesis that there's no difference between X and Y means this would need to be 0. And this is basically how this formula then collapses to t equals mx minus my divided by this standard deviation of those differences that we have established based on the variability of each respective sample that has contributed to the estimate of the variability we would see in these differences derived from those random samples that we've drawn. So this is how we're characterizing our differences, our distribution, comparison distribution of these differences between the sample means. So this being said, if we were now to test this against an alpha level of 5%, we essentially know that our critical t essentially is now to be seen from the t-score table. We know that if we are looking at a p-value of 5%, we essentially have a critical degree of freedom with a degree of freedom of 7. We have a critical t of 2.36. So 2.36 essentially is our critical t. So what does this mean? So if we know that the difference here is, oh no, let's do the t calculation first. So we do a t calculation is now simply the mean of y minus the mean of, oh no, wrong. Well, so here's mean of x minus mean of y. It comes to the same thing because it's a two-sided test, but let's follow the format of Norn and Heinzen. So we have mean x minus mean y well, essentially -0, which is just a formality logically. But we're basically dividing this now through our variability or the standard deviation of these differences between the sample means. So now this difference divided by the standard deviation of the differences between the sample means will get us to a t, which is here estimated as -2.44. And oops, overly sensitive mouse. So this being said, when we would map this out now in a normal distribution, we have our distribution here to both sides with 95% within the boundaries of a t-score of -2.36 and +2.36. Everything exceeding this t will be a type 1 error. So basically, we will basically indicate what indicates the boundaries within which the type 1 error is smaller than 5%. So that means that a t smaller than 2.36 will basically indicate it's a significant difference. So this being said, we are rejecting our null hypothesis now. So this is essentially how we're getting to our hypothesis test. So now we know we're rejecting the null. What do we want to know next? We want to establish the boundaries of a 95% confidence interval. And this is, to some extent, once we have done the t-test, this is more or less a formality to some extent, because we know already it's significant. But for reporting, you would always report the 95% confidence intervals. You remember the statement that Nolan and Heinz made about the new statistics, where you always report confidence intervals. And indeed, the confidence intervals give you an idea about the distribution between these differences. So if we have a difference between the mean of x and the mean of y of -1.5, we essentially need to establish now our 95% confidence interval around this difference. So this would be the mean minus our critical t, which indicates a 5% alpha, multiplied by our standard deviation of those differences. So that would give us a lower limit of -2.95 and an upper limit of 2.36 multiplied by standard deviation of -0.047. So that basically is corresponding with our test statistics and our interpretation of the test statistic, that this is significantly different. Because if this were not significant, the 95% confidence interval would not contain, or would contain 0. Since it does not contain 0, we can here confidently, at a confidence level of 5%, or at an alpha of 5%, say that we're seeing at this alpha level of 5% that this is significantly different. So this is the interpretation, and this is also how you would essentially be reporting it. So you would say that there's a difference of -1.5, and within a 95% confidence interval of -2.96 or 2.95 to -0.05, 0.47. So any questions on this? I know it's a little bit more complex arithmetically, but it follows a very logical outline of how this is to be approached. So if no questions, we can go to the last bullet point, which is essentially the effect size. As we know, sample size affects the probability of rejecting And sample size then essentially also renders clinically not meaningful results as being significant. Therefore, we want to take this effect of the sample size out, and we're basically quantifying it as an effect size by dividing it by the standard deviation rather than the standard error of the mean, which is strongly affected by the sample size. Therefore, we have a calculation of the difference. So this minus this. We need to put this now into brackets. And 35 is now correct. This is N12. So J12 minus N12 divided by the standard deviation of the differences. So now wrong. So it's actually, yeah, so it's the pooled variance, it's the SQRT of this pooled variance gets us to the standard deviation of these samples, the pooled standard deviation, rather than the standard error of the mean. Sorry, my bad. So this is now negative. As we know, the effect size is independent of a directional, of a sign. So we need to set this to an absolute value, and setting it to an absolute value gives us an effect size of 1.63, which essentially is now a large effect size, which is not surprising, basically because 4 versus 2.5 is a considerably large difference, giving the small numerical value. And in the light of the variability, this also turned out to be significant, and this is a large effect size. So this would, if we go further here on the slides, we have done now, this would be the reporting, how you would report the t-scores. So you basically report the t-scores with parentheses of the degrees of freedom. You state a respective t-score, which is minus 2.44. As we've calculated, its p-value smaller than 5%. We know that. And then we go on to calculate our 95% confidence interval, which is calculated as we've calculated it here. This is our actual critical t, basically get us to our estimate of the 95% confidence interval, and then gets us here to the estimation of these confidence intervals, and here to the numerical values, and then lastly here to the calculation of our effect size. So now the effect size, we know the conventions are the same. The 0.2 to 0.5 is a small effect size, 0.5 to 0.8 is medium, greater than 0.5 results in an overlap of 53% or less, and thereby is a large effect size. So lastly, I would like to introduce you to a new formula. This is an Excel function, internal Excel function, that basically allows the estimation of the exact p-value. The function essentially is as simple as you could imagine it. It's basically equals t.test, allows you to calculate now the p-values based on the t-distribution. If you click here on the formula builder, it basically opens up here the respective mask where you can enter this information. So you have here array 1, array 2, which we know array 1 is our $10 wine, array 2 is our $90 wine, the purportedly $90 expensive wine. It asks us next for the tails. So since this is a two-tailed hypothesis test, so we didn't hypothesize any direction. We didn't hypothesize whether the $90 or the population, which was told that the wine is $90, actually would rate higher. So we didn't give a direction to our hypothesis. And we essentially were looking now at a two-tailed hypothesis test. So the tail, the number of tails is 2. And then lastly, we need to select the type of t-test. So we have here, and this is down here in the description, we have the type of t-tests that can be conducted using this function. So we have a paired t-test. This would be if both of these populations would be before and after, as you know. Then we have a two-sample with equal variance, which is labeled here as homoscedastic. Homoscedasticity indicates that there's an equal variance between the groups. Will be important when we talk about analysis of variance in 2 weeks. And then we have a two-sample t-test with an unequal variance. And this is basically the example we're looking at here. So we know that there's a different sample size in both of these populations, which will prompt us to essentially assume an unequal variance. So we, and this is clear when we look at proportions. So we enter 3, then we click on done, and we get as an estimate here 4.1 p-value, 4.1% of p-value, which essentially is smaller than our 5% alpha, which essentially confirms our hypothesis that this is a significant difference. So this is essentially the calculation. So let's quickly recap this. Any questions on this? Any questions so far? If not, then let's quickly recap this analysis. So we have 2 groups. Both groups are being told they're drinking a different quality of wine. They're either drinking $10 or $90. We have 4 liking or 4 ratings from the $10 group. We have 5 ratings from 5 individuals in the $90 wine group. We get 2 different means. We get 2 different sum of squares, which are substantially different. We get 2 different variances based on these sum of squares that are different, which indicates that there's a different level of variability between both groups. And then essentially we are calculating a pooled variance based on the proportional weight between those 2 groups that are basically reflected by the proportions of the degrees of freedom in reference to the total degrees of freedom. From there, we basically get to a squared pooled difference, and a variance of this difference, and then lastly to a standard deviation of these differences that essentially resembles and is being used as our standard error of the mean for the hypothesis testing. So we're basically standardizing this distribution of the differences between the sample means. With a t that is greater than our critical t, we essentially getting to the conclusion that we are meant to reject the null hypothesis, because our differences basically is outside of a 95% confidence interval surrounding 0. So we're basically, we have now finally computed here the confidence interval, which basically shows that 0 is not contained within the 95% confidence interval surrounding our mean difference between the two groups. That confirms our interpretation that there's a significant different liking or rating. And then lastly, we are looking at an effect size to take out the effect of the sample size and essentially get an estimate that is reflecting in more detail, putting more weight back on the difference. That basically is here a large effect size. And lastly, we have confirmed our insight that the null is to be rejected by calculating the exact p-value within which we are rejecting. So that means the rest risk of the probability of a type 1 error in our rejection, which is here at 4%. So with a 4% probability of making an error, we are rejecting the null hypothesis that these 2 means, these mean ratings, are identical between those groups. So, okay, So that was essentially our independent sample t-test. Any questions from anybody? Or was it somewhat clear? I know it's a little bit more complicated, but we will repeat this next week. We will go through the material again and also see the more holistic picture of what the t-distribution essentially is all about. And that should prepare us well also for the quiz that we're going to have very soon too. So lastly, we're briefly talking about the Bayesian approach to data analysis, which essentially represents a shift in statistical thinking. So it's more intuitive and straightforward than hypothesis testing by including prior beliefs. And so essentially the prior belief in the example of the wine rating is essentially what I stated at the beginning. So you have a prior belief, which is often not very accurately quantified, but there was a prior belief that we have that those that are being told that they're drinking a more expensive wine, although they drank the same wine as those individuals in the $10 group, they will rate it higher. So this is based on anecdotal experience. So in that context, not well quantified. But if you have the means, if you have the possibilities to quantify something beforehand in a certain shape or form, you essentially can make conclusions about differences that you see in your sample based on your prior belief and on the data that you have available, corroborating your prior belief. A very good example in this context. So hypothesis testing tests yes or no, and that can be wrong. That you say yes, so you reject something that actually you shouldn't have rejected. That's your type 1 error. That's a false positive. Or you fail to reject something that you actually should have rejected. That's your false negative, right? A very, very common scenario in which Bayesian statistics are being used and Bayesian analyses are used is in diagnostic testing, for example. Let's assume you want to quantify or you want to utilize a diagnostic test, estimating or diagnosing diabetes. And if you use this test with a certain threshold in a certain population, that is, I don't know, you just go out on the street and you test randomly a sample within the streets of New York. And you would, in a perfect world, you would test everybody with diabetes. And you say, let's say the prevalence of diabetes is 10%. So you would find in a sample of 100, you would find in a perfect world 10 individuals. So now you have with tests, you have a little bit of a problem. You have false positives and false negatives. Where false negatives is, for example, you are not testing somebody as positive who actually is a diabetic. Where a false positive, so that would be a false negative. A false positive would be you're testing somebody who doesn't have diabetes and you diagnose him as a diabetic. So that's a false positive. So false negatives and false positives in diagnostic testing are actually a huge problem because they determine your sensitivity and specificity. Sensitivity and specificity in diagnostic testing is actually a test characteristic that helps you to quantify the quality of a test, so the predictive quality of a test. So now this is one way to quantify the test characteristics. If you're utilizing test characteristics in different populations, you can also quantify this as what is called a positive and negative predictive value, which is actually the predictive value of your statement. This individual is a diabetic, or this individual is not a diabetic, based on the prevalence in the population. Because your statement that this individual is not a diabetic has a different weight and a different probability of being wrong if you utilize it in a population where you know the prevalence of diabetes would be high. So if you use a test and you're doing that in a waiting room of a diabetes clinic, and you basically, your test shows you this is not a diabetic, this is a whole different statement than going out in the streets of New York and testing randomly any individual that you encounter and saying this is not a diabetic. So this is positive and negative predictive value, and this is informed by that prior belief. And in diagnostic testing, this is called conditional probability. And this is basically where a probability of a false positive or false negative in a binary decision-making process is informed by a prior belief based on a probability that you know beforehand, before you even conduct your test. And this is where Bayesian analysis essentially is having a lot of weight in this approach. And so Bayesian analysis are used in many contexts, and they have been suggested to also replace hypothesis testing. And I'm not going to go into much detail in this regard, but this is in a nutshell, in a brief description, what Bayesian statistics does entail and for which it's being utilized in the context of medical statistics. Good. Any questions on any of this? Well, if not, then I guess we can conclude for today. And I wish you a nice long weekend and happy Thanksgiving.
Thank you.
Thank you.
Thank you. Bye-bye.
Happy
Thank you.
Thanksgiving.
Happy Thanksgiving.